Alright, section 3.1, introducing the derivative. This is a really exciting section because derivatives are a huge concept in Calc 1. So, I wanted to start off with just the basic limit definition of a derivative. Here on the left you see f prime of x. That's one way to notate the derivative of a function f of x. And we define the derivative as the limit as h approaches 0 of f of x plus h minus f of x divided by h. So what does that mean? Well, if we were looking at 2 points, so suppose we were looking at a point x, and then h away from that we have another point x plus h. Then we'd have 2 points, right? We'd have a point x plus h, f of x plus h. Okay, that's the xy coordinate pair for that point on the graph. And then we'd have the points x, f of x. And perhaps, we were studying this function, we wanted to analyze it. Suppose we wanted to know the average rate of change, whether it's increasing, decreasing, that sort of thing. Well, if we connect these dots and draw a line between the 2 points, the slope of this dashed red line represents the average rate of change of the function between the points x and x plus h. And so that tells us something about the function. First off, here as I've drawn it, it's a positive slope, so we can see that sort of in the long run, the trend is upward, things are increasing. Examples in the real world of when people might do this could be studying the stock market, or maybe this is actually the elevation profile of a hike here that we have. So from point x to point x plus h, maybe they're a mile apart. You'd want to know on average what's the terrain doing? Is it going up? Is it going down? How much is the elevation changing? That sort of thing. Okay, but an average is an average. Okay, it's an estimate. What if we wanted to know this exact slope or the exact steepness at this point here? We could change colors. Okay. Well, that might be useful because we want to know exactly what the rate of change is at that point. The first line that I've drawn is really going to be an approximation of the slope at that point. So how do we get a better approximation of the slope at that point? Well, we can start by collapsing x plus h in towards x, or in other words, letting h go to 0. So if I collapse x plus h in and make h really small, so here's my new x plus h, and now I draw an average rate of change through those 2 points, I have a slightly, arguably closer approximation. And then, you keep going, you keep shrinking you keep shrinking h, and soon enough you're going to have a really nice approximation or a really nice exact answer at x itself. Okay, so a derivative is really giving you the instantaneous slope versus the average rate of change of slope. So let's do an example. Okay, so here we want to use the definition of a derivative that I gave you on the previous page to find dy dx for y equal to 1 over t plus 1. Then we're going to evaluate the derivative at t equal to 1. Okay, well, first off, let me make a small correction here. So we're not finding dy dx, since our function y depends on t's, we are finding dy dt. Okay. So, dy dt is going to equal the limit as h goes to 0 of 1 over t plus h plus 1 minus 1 over t plus 1 over h. And now our goal is to simplify this and let the limit of h go to 0. So hopefully you can see that we can't let h go to 0 yet, because that would cause some division by 0 in the denominator. So we need to algebraically manipulate this first. So the first thing I'm going to do is combine the top two fractions into a single fraction, and then I'll multiply by the reciprocal of the denominator here. So a common denominator would be t plus h plus 1 times t plus 1. So that would give us t plus 1 minus t plus h plus 1 all over t plus h plus 1 multiplied by t plus 1. And then that is all over h. Alright. Well, so division by fractions is multiplication by the reciprocal, so that will give us lim as h goes to 0 of t plus 1 minus, t plus 1 minus t minus h minus 1 all over h times t plus h plus 1 times t plus 1. And now you can see that we get quite a bit of nice cancellation in the numerator, and so this simplifies down to just be minus h over h times t plus h plus 1 times t plus 1. The h's will cancel, the 1 in the numerator, 1 in the denominator, and so we have lim as h goes to 0 of minus 1 over t plus h plus 1 times t plus 1. Okay, so now it's okay to take the limit as h goes to 0, because if we let this h be 0, it doesn't cause any problems. It doesn't cause division by 0. And so if we go ahead and take that limit using direct substitution, we have minus 1 over t plus 1 squared. And so that is the derivative with respect to t. T was our independent variable of our given function, which we started out with 1 over t plus 1. Okay, so there's our derivative. So the second part of this was asking us to evaluate the derivative at t equal to 1. So I'm going to add that into the side here. So at t equal to 1, dy dt evaluated at t equal to 1 is going to equal minus 1 over, well, if t is 1, we'd have 2 squared, which is 4. So this tells us that the slope of the function at 1 is negative 1/4. Okay, and you know, we can graph that. If we were to graph that really quick here, the function 1 over t plus 1 looks like 1 over t, or 1 over x, but it's been shifted to the left by 1 unit. So got its vertical asymptote at minus 1, and use a different color. Actually, I'm going to erase this a little bit, give myself a little more room. I ran out of pages, so I can't go forward. We'll graph it in red. Okay, so you can kind of see, you know, if we're looking at t values of 1, we do indeed have a negative slope at this point. Okay, and so our answer makes sense. Alright, well that's all for now.